Thank you. So welcome to my tutorial. So I will start, first part will be on the basics of macro-electromechanical systems. So I work in this field for 30 years, so I try to give a very, what you should do, just the minimum you should know. Normally, lecture, second part will be on fabrication. These two lectures, normally you need several tens hours, so I try to condense, so it will be very dense. So I will start by giving some general definition on macro-electromechanical systems, by describing the different types, some historical background. I will talk about integration, miniaturization. We'll give some examples of applications, MEMS, and so on. And also I will give you some idea about the current MEMS market and the main industrial players. So what is a macro, nano, opto, electromechanical systems? First, it is a device that includes mechanical nanostructures that can be deformed, that can move, or that can vibrate. Then you must have integrated means for actuating the motion or detecting the motion or deformation of these macro nanostructures. This is the minimum normally that you should have to call it a macro electromechanical systems. But nowadays you have also broader, more complete macro-electromechanical systems that integrates electronics. So it can be a form of applied application-specific integrated circuits, typically in CMOS technology. As you will know from this workshop, you can have also integrated energy source or management or harvesting. And for the case of opto-electromechanical system, you have also some optical macro components like macro mirrors or other kind of optical devices. So for integrated actuation detection, there are many kinds. I will just give some list. You will have more information in the following lectures. So this name is macro, nano, opto, electromechanical systems, but in some countries they call it macro mechatronics or macro machines, especially in Japan. And nowadays many devices are not actually really macro electromechanical systems, but are called like this if they are multi-physics miniaturized sensors. So from what you can see here, within these old devices, you will need a packaging, and the packaging is, to get good performances, the packaging is as necessary as the device. Often this is a limiting part of the good performances of the final device. So it means that if you want a good device, you don't need just to design a good mechanical structure and actuation detection, but you must have also a good electronics and a good packaging, so you need a concurrent design. So before in the industry, it was separate people and separate services, but nowadays there is more and more a concurrent design approach where you have to make design together of both the MEMS, the electronics and the packaging. So what kind of macrostructure you can find in MEMS? Well, the basic one is beam. So you can have a cantilever beam with an anchor on one end, or the macro bridge where you have an anchor at both ends. So they are suspended structures that can be in any kind of material nowadays. So often they are on silicon with a thin film on it. but not only, as you have seen in the previous talk. It can be in stainless steel or in electric films, it can be metallic. So we have some example of devices made in my institute in the past. So this is aluminum macrobeam, tungsten macrobeam, shape memory alloy macro bridges, and silicon polysilicon macrobeams. These beams can be combined to make springs. Typically, they are combined with plates and beams to make suspended structures. Typically, you can have such kind of structure with a plate that can move like this and spring made of beams. So the square are anchors. And as you see, you can have many kind of configuration of the spring and of the plates. So the most common one are this kind of spring called double folded beam because they have a large linear translation range. This kind also is very popular. You can have also some kind of spring like this that are called serpentine spring. And for a plate like this, often you have this kind of crab leg spring. The shape of the spring really depends on the problem of stress relaxation to avoid buckling and to have a large length in the minimum space. Second component that you can find commonly in MEMS are membranes. So membranes are part of materials all made in the substrate. So they can be a square, rectangular, circular. They can be plain like this, or you can have one with holes or with patterns on it. So especially for piezoelectric devices, you can have this kind of membrane with some patterns of piezoelectric materials and electrodes. So the size can go from a few micron to 1 centimeter, and the minimum thickness is typically 50 nanometers, and you can have membrane in silicon for up to 100 microns or more. So again, some example from my institute in the past. This is membrane of 8 layers membrane of silica and silicon nitride to make a Bragg mirror for MEMS. This is a molybdenum membrane and transparent, UV transparent silicon oxynitride membrane. So now let's talk about actuation. So actuation, the goal is to generate deformation, displacement, motion, or vibration of this kind of macro nanostructures. There are many ways to do that, but the most common one you can find in this product, that means they really work, is electrostatic actuation. So the principle is very simple. When you have two plates, metallic plate or conductive plate, and you apply voltage, they attract each other. So you generate a displacement of the plate, and if you apply alternative voltage, you generate vibration of the plate. For piezoelectric actuation, I will not insist because all this workshop is about piezoelectric film actuation and transduction. So you apply voltage, you generate a strain, and then general deformation of the device. You can use also electrothermal actuation. So you just pass a current inside the structure, so you have a heating by Joule effect, then the thermal expansion. Of course, thermal expansion is very weak, so you have to use some levering mechanism to get, if you need, a large displacement. And finally, you can use electromagnetic actuation based on Lorentz force, where you pass a current inside the structure and you have external magnetic field, typically with a magnet or with a microcoil, or you can have pass a current in microcoil and your device is inside the coil and is magnetic. So this kind of actuation is not so common, even if it is in the category of a common actuation method. Why? Because you need a large current, so you have a large consumption, energy consumption. But the advantage, one of the unique advantages of this technique is that you can have very large range of actuation. For electrostatic, it's very good for when you have a small distance between the electrodes, so it's for rather limited actuation range, but with almost no consumption. For piezoelectric actuation is more when you need a large force. In general way, when you use material properties, you can generate large forces, but you have limited displacement. Same for electrothermal. So, in the laboratories, you will find much more actuation techniques. So, some are often they are specific to some application or some device. So, one is that is very popular nowadays in devices for fundamental physics is optomechanical, because you have no contact. So, because you have no contact, you can have very high quality factor of resonance structures. So the principle is that you shine a light beam on the structure, and you can have a different mechanism generated by light, like heating by absorption. So in that case, it's like electrothermal, you just expand the material. You can have photostriction, it's based on the polarization of material in semiconductors. When you shine light, you create electron pair all in the material, and this generates a polarization and then a deformation of the material. Or you can have a radiation pressure, which is transfer of momentum of photon to the structure. So these is not very powerful actuation. For example, radiation pressure is about piconewton for 1 milliwatt of a light beam. But you can generate this without large information of the material and of the device. So it's much used for quantum devices, for example. And it can be applied without contact at liquid nitrogen or helium temperature. So this is good for very high performances devices. Another mechanism that can be used is magnetostriction. So it is based on the fact that when you apply a magnetic film, you have a shrinking of the material, of the magnetic material. So if you select some specific material, this effect can be large, not so large, but it can be sufficient to generate deformation and actuation. So it is negative, it means that when you apply magnetic field, you have a shrinking. Instead of when you heat, you have expansion. You can also use solid-solid phase transition like shape memory alloys or materials with insulator metal transition or any phase change. Generally, with phase change in the material, you have also change of structure and change of generation of stress and strain. You can also use liquid gas and liquid solid phase transition, for example, from a liquid to vapor, making a bubble, or from liquid to solid. So this is used for in some MEMS mechanism to make a lift structure from a solder in liquid form. When it becomes solid, it generates strain that lift the structures. Of course, you can use standard piezoelectric material, like you will see in this workshop, but you can also use semiconductors that are piezoelectric, like 3-5 semiconductors. This is not very common because technology is difficult. If you have more information, you can ask to one of the attendees here. And you have also many other kinds of materials, like energetic materials are almost like explosive. So these are layers of, like if I remember, aluminum and nickel layers. If you initiate some reaction, then you have a very high generation of heat that propagates, like an explosive. So as you see, there are a large range of possibilities, but not always can be applied in a final product for large volume, but for some specific application, you can think of using any kind of phosphones. For sensing, same if you want to integrate detection, you can. The role is to detect strain, displacement, motion, vibration, and macro nanostructures. So the most common ones are just the reverse of the most common actuation techniques. So in an electrostatic domain, you can use capacitive detection. So if you have two electrodes, when they move, the capacitance is changing. So you can just detect the variation of capacity. You can use piezoresistive detection. So it's based on the fact that if you take a metallic or semiconductor resistor, when you change the dimension, you will change also the resistance and the piezoresistivity of the material. So you can detect the stress or strength, is stress, sorry for long writing, from the change of electrical resistance. So for metal films, this is mainly due to change of dimension, and for semiconductors, the effect is mainly due to the change of the resistivity, to the change of population, the conduction, and the valence band of carriers. You can use piezoelectric, inverse piezoelectric effect. It means that when you have a strain applied to a piezoelectric material, charge are generated on the surfaces. And you can use also inductive displacement, where from a displacement you join change of inductance of reluctance or change of eddy current. So these are the most common ones. Less common ones is magnetorestriction. So inverse magnetorestriction means that when you have apply strength to magnetic material, you change the magnetic properties. You can use a specific geometry for piezoresistive detection, like nanowires or very tiny structures. You can use some specific inductive technology to make use of magnetomotrice force. This is mainly proposed. This was mainly proposed for nano-electromechanical structures. So this is for strain detection. For displacement detection, you can use almost any kind of optical technique. So based on variation of intensity, of deflection, of interferences. So you can use acoustic detection. You can use tunnel effect between electrodes, field emission, thermal detection, and so on. So we will not detail all this kind of detection technique. In the other lectures of this ENHANCE workshop, you will have information of piezoelectric, electrostatic actuation and detection. Maybe they will talk about also the other kind of actuation and detection techniques. So, from these kind of devices with mechanical structures and all this kind of actuation and detection method, you can do plenty of devices. So generally they are divided in all these categories. So you have macro nanosensors, mainly for physical and chemical sensors. Macro actuators, where you just generate motion, like motors or translators. When you have optical function or optical devices inside that call optical MEMS or opto-electromechanical systems. So optical MEMS is more MEMS with optical application, and MEMS is more MEMS with optical devices inside. When you go to high frequency range, they are called RF MEMS. This is the same for MEMS for RF application or microwave application, or MEMS that includes RF components like antennas or filters and things like this. As you know, in the last year there is a large rise of application for health and bioanalysis. So they are typically divided in two categories: the macrophysics system, lab chip, and macro data analysis systems. So even they are often called MEMS, but actually often there are no moving parts, no mechanical parts. And you can also call them bio-MEMS. So in that case, you have really some detection based on micro-electromechanical systems. There is a specific category for the MEMS based on magnetic or electromagnetic actuation or detection called MEMS. And all of these are MEMS, depending on the size. MEMS, if the size is on micrometer range, and MEMS is a mechanical structure of dimension below 1 micron. So all these devices cover a very large range of material, dimension, and fabrication technologies. And now the trend is to mix all these kind of devices to make more intelligent devices. So it can be on the same chip, on different chip, on the same surface, or on chips that are superimposed for 3D by 3D technologies. So a little bit information about the background. So often the first electromechanical device cited is one from Nathanson in the 60s. Then there was a large gap of 10 years where nobody used any electromechanical systems. Then it was started to build some accelerometers in the mid-70s. And it was based here, some technology useful for MEMS was started to be developed, like silicon, glass bonding, and other technologies. So the first MEMS was at the end of the 70s. And the famous paper is a paper by Peterson, if I remember well, I don't remember his company, Texas Instruments, I think, where he wrote a famous paper describing the use of silicon as a mechanical materials in devices. So it was in the 80s. From 80s to 2000, this was a development of technology and appearance of the various types of devices. So you see, macrophysics, lab on chip for physics and bio was mid-90s. The MEMS, the word MEMS, was born just before 90s, and the MEMS started in the year 2000. So you see there are mainly three phases: the basics, the new material processes, and the beginning of commercialization. And since this 80s, the market and application is growing regularly, very fast. And nowadays, for your future, the future is to add new integration technology and packaging technology, take benefit of new detection and actuation principles to make devices that are not only doing one function but are multifunction, as I explained in the previous talk, but in a single device on several single integrated macro systems. So about integration, you have basically three kinds of integration. Integration that is called monolithic, where you have the sensor electronics on the same chip. This is typically for MEMS based on CMOS technology. So this is an example of old example of accelerometer from NUC devices. This was one of the most older macro systems with integrated electronics. So you see the sensor is this size and all the rest is electronics. Second category is hybrid integration for horizontal integration, where you have different chips on the same package. So typically one for MEMS, one for electronics, maybe one for memory or for another sensing devices. You have some example here. So the minimum is sensor and the integrated circuit for driving the sensor. And the new generation, the trend is to do vertical integration. It means that you have MEMS on top of CMOS, and you can have different layers of electronics and MEMS. So typically for macro bolometers, for infrared cameras, this is almost always like this. So be aware that making a small sensing structure doesn't mean a small device. I'll give you an example. So the size of macro nanostructure is not the size of the device. First, because electronics can be much larger than the sensing part. And secondly, you need some connection. And the connection pad is typically 100 by 100 micron or more. And you need typically one for two for the input, two for the output, two for the power supply minimum. So it means that making a small structure doesn't mean making a small sensor, except if your sensor can measure plenty of things. So we see very often this mistake in publication. They say, I'm going from MEMS to NEMS and I will be able to do things very small that have never been made. Often this is not at all true. This is a mass sensor. You see, the sensing part is this small part. All the rest are pads and electronics. So take care of this. And making small is not always necessary and useful. Of course, in general way, when you reduce the size of the structure, you get a better sensitivity. But you have also some things that you have to think. First, you have generally, when you reduce the size, you have a lower signal level. So it means noise, and it means also more complex and more expensive electronics. You have also typically a reduction of the measurement range, because the noise level is more or less similar, and you reduce the range because you can become nonlinear, or as explained this morning, you can break the structure. You increase the ratio of surface to volume. So it means that you will be more sensitive to environment and to sample history. Sometimes this is what you are looking for. If you are looking for an environment sensor, this is a good point. But generally, you don't like your sensor to have different properties today and tomorrow. So it means that generally you have to take care that it can lead to lower repeatability and reliability. When you are doing resonant structure, mechanical resonators, when you reduce size, you have typically a reduction of the Q factor, quality factor. So of the performances, of the stability, of the resolution, and so on. When you have a smaller surface, if you're doing a gas sensor, biosensor, chemical sensor, environment sensor, it means that you have a lower capture probability of molecules. If you are under, typically you need also to detect different kind of gases or biospaces, so you will need array. So this will generate statistical noise and also increase of the size, because if you have a single device for gas, chemical, biosensor, generally you will be able to do only a specific measurement by assuming that there is no other spaces. And also when you have making small, you will use more costly equipment for fabrication, process control and measurement. And finally, when you make it small, of course the accuracy of dimension is lower. So you will have, you can have lower repeatability requirement of specific architecture for electronics, for redundancy, to take into account that you have variation of the properties of material and of the structure. So it means that when you are reducing the size of the device, don't do it for fun. You have to think that when you will reduce, maybe your device will be will have worse performances. So the problem, of course, when you are in a research laboratory is that to get money, you have to go to nano, to a thing like this. So this is a problem that because the people who give money, they don't know all these kind of things. But if you are making device, you can make some small for the money and some maybe larger for the performances. So application, nowadays you have a MEMS, macroelectromechanical system, in almost all everyday application for telecommunication, for variable capacitance and inductances, for switching antenna and so on, for filters. In transportation, in a modern car, you have almost 80 miniaturized sensors. So you have everywhere for the motor, control of the seat, of the light, of everything. In aeronautics, for navigation, for accelerators, for pressure and so on. In space, in defense, for the weapons to guide them. In medical application, for brain, for disease. In biology, for chemistry, there are mainly gas sensors, but also to build macro reactors. In consumer goods, in your smartphone, you have plenty of MEMS and macro sensors, but also in printers, in displays. So the most famous MEMS device, the first one is what you can find in the digital projector. In games, and also in your home, as explained this morning, maybe the future home, you cannot move without spying all your body and your mind in the future, but at least the air and water. So some example. So how to detect something with a beam, with a continuous beam. For example, for temperature sensor or radiation sensor, you just have can have a behavior with a sensitive beam to temperature. When you have a difference of temperature, we have some strain because of the metallic effect. So it will bend, and if you can detect the motion, you can detect the temperature. If it is a layer sensitive to radiation, also you can detect radiation. Of course, you can use it simply as a mechanical sensor. So if you apply pressure, acceleration, and so on, you will have deformation, vibration, displacement of the beam. You can detect magnetic field by putting a magnetic layer. You can make macro nano resonators by vibrating the structure, and it can be used for mass sensing, for filtering signals, or for environment sensors. You can use it also for chemical reaction. So when you have chemical reaction, you can generate heat or generate strain. So it will deform the device. You can use it as a for a chemical sensor. You can use it for heat sensing. So if you have a generating heat, you will generate a difference of temperature that you can use to deform beam. This can be used in air, in vacuum, but also in liquid for biosensors. So for biosensor, you can use a change of properties of conduction. You can use a change of mass, or you can use a change of strain. So for membrane, the main application, you can use it as a mechanical function, as a deformable structure. This is used in microphone, pressure sensors, and valves. You can use the membrane as a mirror or diode for tunable optical cavity, for deformable adaptive mirror for space application. You can use the membrane as an electrical function, as a moving electrode for insulation. So, for example, for variable capacitances, this is a plate or a membrane that is available. You can use it for a thermal function. It can be insulating support, suspended insulating support for thermal microsensor, for microheaters, for microbolometers, for cameras. And finally, it can be a window, just a window, for various kinds of beams, for electron beams and beams, or for X-ray. So of course, for electron and beam, it will be very ultra thin. For microactuators, I'll give you a few examples. So one of the oldest microactors are micropump. So you see a cross section of a micropump with 4 wafers. So here you have a membrane that can be actuated by electrostatic wave from the gap here. So you apply voltage between here and here. This will move the membrane, so this will change its volume. So if you have some pressure here, it will open the inlet valve. And then if you stop actuation, this valve will close, and with the pressure, if you actuate again, you can have the fluid going from there to there. This is exactly what is the pump. Here are some example of motors, electrostatic motors. So this step motor where you apply voltage, you have a rotor here, stator here, you apply voltage successively to the pads here that makes rotate the rotor. So you see the size compared to match. This was a fashion in the 90s to make micromotors, but actually these are very nice. They can go up to 10,000 turns per minute, but they have no force, so they cannot drive anything except themselves. So, but they are very good example of development of technology of MEMS. They were very useful to investigate various problems you can find in MEMS, like friction, like stiction, and so on. But I'm not aware of almost any application of micromotors in very small ones in existing devices, so maybe in printer heads. Some example of electrothermal microactors. So for example, this is well known where you have a very thin beam and very large beam. When you have a current going through the small beam, it will expand. This one will not expand, and this will generate a lateral force, as you see here. Another example is a chevron actuator. So when you hit, it will be like the, I don't know the English name of this musical instrument, but this will expand and will push here at the end of this part. So it's, you have anchor here, you pass the current in this structure, you will expand and will move on this direction. Squash drive is like a worm, is like the motion of worms. So it's like this. When you apply a voltage, it will go like this. You stop it, and it will go like this, exactly like a worm. So the advantage is that there is no limitation of the range. If you have some structure length, it can go for centimeters if you apply alternative voltage. Some example of macro sensors. So one of the most common application for physical sensors are pressure sensors and accelerometers and gyrometers. So I'll give you here some examples. So pressure sensor, diaphragm pressure sensor, you have a membrane. So when you have pressure, you have a hole in the substrate. When you have pressure, you have deformation of the membrane, and you have strain gauge based on piezoelectric effect that detects the deformation of the membrane that is related to the pressure. So you see example of a second glass pressure sensor. Here are some example of macro accelerometer. So I choose one in glass in quartz technology to show that we are not limited to silicon. This is an accelerometer differential. So the principle is that when you have acceleration, here you have a large mass that will stretch the beam here. And the beam is quartz, so it's piezoelectric. You can detect its resonant frequency. And like a chord of an instrument, when you stretch it, the frequency will rise. So from the detection of frequency, it detects the acceleration. And you have another one to compensate for common for temperature compensation or for compensation of other kind of forces. You see example here. This is a 3-axis macro gyrometer that is being studied with Wondera and my institute. So it's based on Coriolis force. So you have you make vibrate the frame here, like you see in yellow, the vibration mode of the frame. When you have a rotation of the device, you will generate a coupling between vibration by Coriolis force. So if there is a rotation along x direction, you will have a vibration of the beam here, y direction of this beam, and with that direction you will have lateral vibration of the beams. Here it's out of plane. So with a single device you can detect when it will work, it should detect rotation speed in 3 directions with a single device. This is an example of a flexible device in polymer. So this is a capacitive pressure sensor array for medical application. For example, for you can put in shoes or to detect the pressure of your feet, to detect mental disease or things like this. This is an example of resonator resonant devices. I've chosen some that are not common to show that by technology you can do almost anything at the present time. Sometimes it's very difficult to do, like a board like this, where you have just a tiny link here. So advantage of this kind of structure is that it can have very high quality factor. You can do rings, suspending rings. So this is used for mainly for optomechanical resonators, because this can be both resonant from the mechanical point of view and also optical resonators. So the ring here is also optical resonator. So eventually you can benefit of both effects and get a quality factor that is a product of the optical quality factor and of the mechanical quality factor. Here are some commercial oscillators used for clocks, for reference clock from Saclay company. So on the same wafer, you you can see there are different kind of resonators for different kind of frequency, so in a minimal space. Actually, in all the smartphone, what was limiting was the quartz resonator for clock, because the quartz resonator is very big. And nowadays, some of them are probably replaced by silicon resonators. This very simple mass sensor, a beam, as you explained this morning. If you make triangular beam, you have a more homogeneous stress distribution, and you can put here a pad that can receive specific biologic species for detecting biosensors. Here are some vibration energy harvesters that are totally mechanic, electrostatic. Probably my colleagues, Elie Lefebvre, will talk about this one in the following lectures. Now some example of MEMS. You have a digital mirror display that you can find in this kind of system. So this is a digital mirror that can have two positions, and if you associate with a beam, you can project the color you like. If you do it very rapidly and you have a matrix, you can generate image that you see on the screen. This is a Fourier transform spectrometer. So you see, this is like an optical system made from silicon parts. So you have mirrors, lenses, and so on, and you can build it like an optical bench, but very small. This is an example of a physical device with optical detection. So this is here you have the beam that moves in the middle, and here you have two broad mirrors made of silicon and air. So when you change beam position, you will change the cavity, and you can detect the motion. This is a tunable Fabry-Perot filter. So you see there are very specific beam for suspension, the part that is moving out of plane. And you can even do a totally integrated microscope or macro devices, optical macro devices. Here is optical quantum tomography probe. You see it can be very small if you integrate both the actuation, the lens, everything. Two examples of nano-electromechanical systems. So the silicon carbide mass sensor. This is just a bridge, vibrating bridge, but it is very small, so it can detect very low mass. Sorry. So down to attogram, and you see just a variation of 2.5 10⁻18 gram gives a frequency variation of 3 kHz, so it's easy to detect. And the record was made by using a carbon nanotube, and they could detect a septogram. So it's very low mass, but it's mainly a lab experiment, because in practice, any molecule you have in the air is a much larger weight. You can detect very low amount of charges also. Typically it's a bridge, and from the variation of charge on the bridge, you can detect them from the variation of resonance frequency, and you can detect charges below the current of 1 electron. You can combine macro systems and nano structures called macro MEMS. So this is an example of a big MEMS device with detection with a nanowire that is just here. No, actually it is here. So you combine the advantage of a small section of the nanostructure, so it's very sensitive from a mechanical point of view, and a large actuator that can be made in MEMS technology. This was used also for magnetometers and various other kind of sensors, especially by CNRS in the south of France. Concerning biosensor, chemical sensor, and microfluidic sensors, there are a very large range. I can give you some very different examples. So Prof that you put in the brain, it's used in practice for Parkinson's disease. So by applying a specific signal, you can prevent the people from shaking. And also there is a various European project to develop this kind of probes to get a signal from the brain, from neurons, for various kind of diagnostic purpose of brain disease. This example of nanowire-based chemical biosensor. So you have electrodes here, dielectric, and the semiconductors. That can be just a small track of semiconductors. So it's an inverse semiconductor. You have a source and drain electrode. When you have you put some specific receptor, biological receptor, so that can select the target species that are linked. Only them are linked on the receptors if you do the right surface treatment. And when you have this link, it will change the charge on the surface charge, so it will do some depletion of the semiconductors. If it is suspended, you can use also variation of mass or of strain. This is an example of a lab on chip, so you have channels to transport, to mix, to do what, every kind of operation on fluids for bio, and you can add also some part where you can do some detection or some heating and anything. So this kind of device is called lab on chip or macro total analyzing structure. On a kind of medical sensor, some example, you can detect disease from breath. So this is more like a gas sensor. From you can have implanted in the body for detection of heart rate. You can detect also glucose or oxygen from by external way, by optical way. You can use any kind of technology, physical, optical, electrical, chemical, biological, in medical field. So the market, so it gives you the one in 2014, distribution between different type of MEMS and sensors in 2014 and 2019. So what you can see is that there is a large increase of the microfluidics part, both for application and for research. You see it was like this, now it's like this. But still a small remains about 25–30% of the whole field of macro systems. So it will be available on the website, so if you are interested, you can look in more details. So some trends of the new ones. So it's only for large volume application. You know, the people doing market studies, they are not inserted in small devices for niche application. They want large volume, big companies. So this is not representative of all MEMS market, to my opinion. It's mainly for large volume application. So this one are the ones that are common nowadays: filters, pressure sensor, oximeter, gyroscope. Actually, since the 80s, these are the largest part of MEMS activity, and still much work or research work and development, both in labs and in industry. New ones that are emerging are microphone, speakers, compass, zoom for smartphones. So most of them are the one you can find in smartphone. So energy harvesting devices, speakers, and so on. So this is also a trend of the market, but in big you have, this is a percentage of the growth rate. This is the annual growth rate of the MEMS field, depending on the type. And larger is the round, larger is the market part. So you see physical sensors are still a large part of RF MEMS, and physical sensors are still a large part of the market. Microfluidics is increasing, 20%, but still a small part. So the future is everywhere, actually. It's up to you. These are the companies, 20 top MEMS manufacturers. So in terms of money, so you see there are some very large players in the USA, Germany, France, USA, and also many Asian companies. So this is just a small part. Actually, there are many startups and small and medium companies all around the world for very specific application. For foundries, so the difference between foundries and companies, they do everything, design, fabrication, and so on. Foundry is the one that provide fabrication process for external designers. So you find different type of companies, and you will see from various. So this one is in Dow. You know, TSMC is the world leader almost in electronics, and foundry actually is not so good position. So it doesn't mean that if you are good in MEMS, you're not necessarily the same companies that are good in microelectronics. I mean, from the money point of view. So I give you some list of research laboratories. So it's not exhaustive. There are so many laboratories, but I try to give some ideas in Europe, because this is a long project. I put some more details in Europe. So if you are interested, you will be able to read. And I gave also a list of books of MEMS. So this is a very broad field, so of course there are a large amount of books available. Same for conferences. You have general conferences like MEMS, transducers, Eurosensor, ultra-pulling sensors. And after, depending on your application, or if you are more on the material side, on the electronic side, design side, you have also plenty of other conferences. I give you the top reviews, but same, it depends on your device. This is the end of this first part.